In section 3.1, we begin a new chapter where we will study the intricate relationships between the 6 basic trigonometric functions. We'll do this by studying basic identities. In section 3.1.1, we will examine the reciprocal and Pythagorean identities. At this point, you may be wondering, what is an identity? So let's look at the definition. An identity is an equation that is satisfied by every number for which both sides are defined. Now, if that definition doesn't clarify the concept, let me give you an example from algebra. An example of an algebraic identity would look something like this: x equals 3x minus 2x. Notice that on both sides of the equation, we have two expressions that look different. However, when I simplify the right side of the equation, we can see that we would get identically the same thing that we have on the left side. So the right side is the left side in disguise. A trigonometric identity will express a similar relationship using trigonometric functions. Now, you already are familiar with the basic reciprocal identities, so let's repeat those here. You've already learned that sine of x is the reciprocal of cosecant of x. That is, sine of x equals 1 over cosecant of x. Similarly, cosecant of x is the reciprocal of sine. That is, cosecant of x is equal to 1 over sine of x. Both of these equations are identities. That is, they represent the same expression in different forms. Continuing, cosine of x is equal to 1 over secant of x, and secant of x is equal to 1 over cosine of x. Continuing, tangent of x is equal to 1 over cotangent of x, and cotangent of x is equal to 1 over tangent of x. Those are our basic reciprocal identities. Now, the great thing about identities is that if you know these three and you can manipulate those equations, then you can also generate these three identities. So even though it looks like we have a list of 6 formulas here, really knowing the first 3 basic identities will naturally yield the second 3 identities. To this list of 6 reciprocal identities, we're going to add 2 identities which express tangent and cotangent in terms of sine and cosine. Now, to understand where these next 2 come from, let's review the ratio definition of our trig functions. We learned that if alpha is an angle on the unit circle, then sine of alpha is equal to the y-coordinate, cosine of alpha is equal to the x-coordinate, and tangent of alpha is equal to y divided by x. Now, because sine of alpha is equal to y and cosine of alpha is equal to x, we can see that tangent is the ratio of sine to cosine. So we could fill out our identity here. Tangent of x is equal to sine of x over cosine of x. And because we know that cotangent is the reciprocal of tangent, cotangent of x then could be defined as cosine of x over sine of x. Within these 8 equations, we have a list of 6 reciprocal identities and 2 identities that express tangent and cotangent in terms of sine and cosine. Let's also introduce the famous Pythagorean identities. These are incredibly useful, and you'll see them pop up in all kinds of problems. You are already familiar with the first Pythagorean identity from material we covered previously. The first Pythagorean identity looks something like this: sine squared of x plus cosine squared of x equals 1. Though we proved this identity previously, we can review the source of this identity by recognizing that a point on the unit circle has horizontal segment given by cosine, vertical segment given by sine. If we assimilate that into a right triangle, the hypotenuse of that right triangle would be the radius of the unit circle, or 1. So essentially, we're just applying the Pythagorean theorem to a triangle on a unit circle. From this basic Pythagorean identity, we can then manipulate this equation to generate two more Pythagorean identities. So I'm going to start by copying down the fundamental identity. Then I'm going to manipulate this identity to generate another identity. I'll begin by dividing all three of these terms by cosine squared of x. Notice if we apply the same operation to all three terms, we are generating an equivalent equation. When we simplify this equation, we can notice right here we have sine squared of x over cosine squared of x. This could be rewritten as sine of x divided by cosine of x quantity squared. In the second term, cosine squared of x divided by cosine squared of x is 1. And on the right side, we could rewrite that as 1 over cosine of x quantity squared. In doing so, we recognize that inside parentheses here, we have sine of x over cosine of x, which we could replace with its equivalent tangent of x. And because the entire expression is squared, we could rewrite that as tangent squared of x. We can drop down the plus 1, and on the right side, we observe that we have 1 over cosine of x. 1 over cosine of x can be replaced with its equivalent secant of x, and then we can square the result. So our second Pythagorean identity is then tangent squared of x plus 1 equals secant squared. Going back to our original Pythagorean identity, we can manipulate it in a similar way to get a third Pythagorean identity. The first time around, we divided by cosine squared of x. This time, I'm going to go back and divide all three terms by sine squared of x and simplify. Though the simplification may be obvious at this point, to show you very clearly, we can of course reduce that first term to 1. We can rewrite the second term as the ratio cosine of x over sine of x quantity squared, and we can rewrite that last term as the fraction 1 over sine of x squared. Then we can see that inside parentheses here, we have the ratio cosine of x over sine of x, and that can be replaced by its equivalent cotangent of x. Because that expression is squared, we could rewrite that as cotangent squared of x. Similarly, on the very right side, we have the expression 1 over sine of x. From this identity, we know that 1 over sine of x is equivalent to cosecant of x. So replacing this with cosecant and squaring, we end up with cosecant squared of x. So here we have three different looking Pythagorean identities, though they all essentially express the same relationship that we see in that first equation. It is important for you to be very familiar with the 11 equations that we have listed here. So take some time to memorize these equations, and you'll really begin to understand the relationships between the trigonometric functions.